Hello all, welcome back to Sri Sai Tech Edu YouTube channel, Read, Lead, Success. I am dealing with the subject Network Analysis and Control Systems. I have already uploaded Module 1 to Module 4 videos in my channel. If you have missed out, please do watch. And in Module 5 also I completed first 3 chapters. From now I am going to start the 4th chapter, that is Nyquistic plot. Under Nyquist plot, there is principle of argument, Nyquist stability criterion, assessment of relative stability using Nyquist criterion. These 3 concepts are there. We will study one by one. In this video, I am going to cover principle of argument. Consider a function, the q of s, that can be expressed in the form of 2 polynomials, and this can be represented as q of s, that is s minus alpha 1, s minus alpha 2, s minus alpha m. Same way, s minus beta 1 to s minus beta n. So s is what? A complex variable which can be written in this way. Then q of s is also complex, so it can be written in u plus jv and represented on the complex q of s plane with coordinates u and v. Okay, equation 8.1, what it indicates is that every point s in the plane, at which q of s is analytic. A function q of s is said to be analytic in the s plane provided function and its derivative exists. The points in which the s plane where function or its derivatives does not exist called the singular points. Where the points which does not exist, the points in which s plane where the function or its derivatives will not exist, then they are called singular points. The poles of a function are singular points. We can find a corresponding point q of s in the q of s plane. Alternatively, it can be stated that the function q of s may maps the point in the s plane into the q of s plane. Since any number of points in the s plane can be mapped into q of s plane, it follows that for a counter in the s plane which does not go through any singular point, there corresponds a counter in the q of s plane. If you see here, figure 8.1, the whole thing what they explained, 8.1 is that, see, these are different points, S1, S2, S3, S4 and S plane. These are arbitrarily chosen. So S plane is what happening as a counter path. If you connect them all, it is becoming a counter. The region to left of the closed counter is considered enclosed with the counter when counter is traversed in the clockwise direction. Thus, the shaded area in figure 8.1a is enclosed by the closed counter. This enclosed area is a closed counter. Corresponding q of s plane counter. Corresponding q of s plane counter is in the form of this. Okay. For this arbitrary s plane counter, this is a corresponding q of s plane counter. Okay. While developing the Nyquist criterion, we are not interested in the exact shape of the q of s plane counter. We are not interested in what? The exact shape. An important fact that concerns us is the encirclement of the origin by the q of s plane counter. To investigate this, consider an s plane counter which is in figure 8.2a. This is a figure which is what is the an s plane counter enclosing a 0 of q of s and corresponding q of s plane counter. S counter enclosing a 0 of q of s means which encloses only one of the zeros, that is one of the zeros of q of s. Say s is equals to alpha 1, one of the zeros. It is encloses only one of the zeros, that is this one. These into marks are what? Are poles. The round marks are what? 0. So it is enclosing only one pole. It means the alpha 1 here is present. No, this is only 1 0 which is present inside. Then while the poles and remaining zeros are distributed in S plane outside the counter. See, these are one pole, this is a 0 0, like that. There are outside the counter. Counter is nothing but the line or the diagram drawn. See, according to the points. So inside one only 1 0 is considered and other zeros and poles are considered outside the counter. As discussed above, for any non-singular point, yes, in the S plane counter, there corresponds a a point q of s on the q of s plane counter. The point q of s is given by what? S minus alpha 1, S minus alpha 2 by S minus beta 1 into S minus beta 2. So on. How many ever are there? Zeros and poles. Alpha 1 is pole 0 and beta 1, beta 2 are poles. So angle of q of s can be written as how? Angle S minus alpha 1, S minus alpha 2 plus so on minus angle S minus beta 1 minus angle S minus beta 2. Whenever you are finding angle, after in the form of numerator and denominator, you can minus this numerator, numerator minus denominator. So it is written that way. Okay. Then you need to add the numerator things minus the denominator things. Okay. Then from figure 8.2a, it is found that as a point S follows the prescribed path, it will follow the prescribed path, that is clockwise direction. If you see here, clockwise direction on the S-plane counter, eventually returning to the starting point, the phasor S minus alpha 1 generates a net angle of what? Minus 2 pi. Okay, 360 degree, nothing but from the starting point to that point itself it is going with a net angle of minus 2 pi, means 2 into 180, 360. So while all other phases generate zero net angles, all other phases contain what? Generate what? Zero net angles. Therefore, the q of s phasor undergoes a net phase change of minus 2 pi. This implies that the tip of the q of s phasor must describe a closed counter about the origin of q of s plane in the clockwise direction. As said earlier, the exact shape of the closed counter q of s is not of interest to us. The shape is not of interest to us. Okay. But it is sufficient for us to observe that this counter encircles the origin once. That circle is what? Observe that the counter encircles what? The origin at least once. If the counter in the S-plane does not enclose any zero or pole. For example, previously what we have seen, if the if the counter encloses a zero, what happens? When it does not enclose any zero or pole, the corresponding counter in the q of s plane will not encircle the origin. Then the q of s plane will not what encircle? It will not encircle the origin. There it will encircle the origin. Here it will not encircle the origin. If the s plane counter encloses two zeros, if it encloses what? Two zeros. Say at s is equals to alpha 1, s is equals to alpha 2, like this, alpha 1, alpha 2. Then the S-plane counter encircles the origin twice. Means it will encircle the origin what? Twice. Means in the clockwise direction as shown in figure 8.3b. See, it is encircle the origin twice. Okay. Encircle the origin twice, 1 and 2. So generalizing, we can say that for each zero of q of s enclosed by the s-plane counter, the corresponding q of s plane counter encircles the origin once in the clockwise direction. See, if there is one zero present, if this is not there, if one zero present in the s-plane, then it will encircle once in the origin. Once it will encircle origin in the clockwise. As here two zeros are present inside the S-plane, that is the what counter, then it is encircling how many times? One time, and again one more time is it is encircling. So you need to remember that the number of zeros inside the counter is equal to number of times it will encircle once in the clockwise direction. Okay. If the S-plane counter encloses a pole, for example, it is enclosing a pole beta 1 and the phasor S minus beta 1 and beta 2 generates an angle of minus 2 pi as S traverses the prescribed path. Since the pole term S minus beta 1 is in the denominator of Q of S, okay, it's in the denominator of Q of S, the Q of S plane counter experiences an angle of plus 2 pi, which means one counterclockwise encirclement of the origin. One counterclockwise, okay, counterclockwise encirclement of the origin. This argument holds for all poles of Q of S. If S plane counter encloses two poles, beta 1 and beta 2, then the Q of S plane counter encircles the origin twice in the counterclockwise direction. Counterclockwise. Counterclockwise means anticlockwise. If it is a pole, it will counterclockwise the direction twice. as there are two poles, 2 times it will counterclock at the origin. Thus, if there are poles and zeros enclosed by the S-plane, then the corresponding Q of S plane counter must encircle the origin Z times in the clockwise direction and P times in the counterclockwise direction. Means Z times means if for example 2 poles are there, 2 times it will do anti-clockwise, and if it is 2 zeros or 3 zeros it is, then it will do 2 or 3 times clockwise direction, resulting in a net encirclement of origin P minus Z. Means what? See, number of poles. For example, if the poles are 3 and zeros are 2, 3 minus 2, 1. One time it is going to do counterclockwise direction. For example, in case of 2 zeros and 4 poles enclosed by the S-plane, the net encirclement of the origin is what? 2 pi into 4 minus 2, means 4 pi. 4 minus 2 is 2, 2 2 is 4, 4 pi. That is 2 clockwise, counterclockwise revolutions are done. And the figure 8.5b, this relation between the enclosure of poles and zeros of Q of S by the S-plane counter and the encirclements of the origin by the Q of S plane counter is commonly known as principle of argument. This is nothing but the principle of argument. We have seen when only 0 is present, when only zeros is present inside the counter, if only zeros are present, it will do clockwise. If only pole is present, then it is anti-clockwise. It is counterclockwise means nothing but anti-clockwise. And if both zeros and poles are present, then it is nothing but you need to minus the poles minus zeros. You will get some value, right? That value number of times. If it is, for example, 2 times it will do anti-clockwise, nothing but counterclockwise. Anti-clockwise is nothing but counterclockwise it is going to do. The example shows what? 2 times. Why? Because it is 4 minus 2. 2 times it is going to encircle the origin. 2 times it is going to encircle the origin. Okay, this is nothing but what? Principle of argument. So this completes the principle of argument. I hope you understood. So much theory is there. Just you should remember what is principle of argument means what? If it is only 1 0 present inside the counter, it will do clockwise direction, and if it is 1 pole present in the counter, it will do anti-clockwise direction once. And if there are both poles and zeros, then you need to minus poles minus zeros. How many you will get? No, for example, 4 minus 2, 2 times it is going to encircle the origin anti-clockwise direction. Okay. So I will stop the video now. In the next video, I will do Nyquistic stability gradient. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.